Good morning, champs! Welcome to the first video in our multivariate calculus series. Today, we're diving into region integrals, specifically double and triple integrals. These are powerful tools in calculus that let us calculate areas and volumes across multiple dimensions, like the secret keys to unlocking the math behind shapes and spaces. They're foundational concepts that we'll build on in future videos. So grab your notebook, get ready, and let's dive into the world of multivariate calculus. All right, let's get into it. Imagine we've got two functions, h of x and g of x, drawn out here. Our goal? To find the area sandwiched between these two curves. We'll call this little area element dA, which breaks down into dy dx. Now, if we want the total area between h of x and g of x over this region, let's call it D. We need to integrate dA across all points in D. So our area calculation is essentially the integral of dA over D. Now that we've set up our area element, let's define the domain, or in other words, the limits of our integration. For the y values, our upper limit is given by h of x and the lower limit by g of x. So we're looking at g of x is less than or equal to y, which is less than or equal to h of x. For x, it's a bit simpler. The upper limit is b, and the lower limit is a, which gives us a is less than or equal to x, which is less than or equal to b. With these limits set, we're ready to dive into the integral. So with our limits in place, we can set up our integral to find the area. Our area formula becomes area equals the double integral from a to b and from g of x to h of x of dy dx. This is essentially our integral of dA over the region D that we defined earlier. Now, in the first step, we'll integrate with respect to y. This simplifies things by giving us area equals the integral from a to b of the expression h of x minus g of x dx. So, by integrating over y first, we end up with a single integral in terms of x that's much easier to handle. All right, let's take a closer look at a special case, when g of x equals 0. Imagine we're only looking at the area between the curve h of x and the x-axis. With g of x set to 0, our area formula simplifies even further. We're left with the classic formula you might remember from school for finding the area under a curve. Area equals the integral from a to b of h of x dx. This approach calculates the area between h of x and the x-axis from x equals a to x equals b. A simple, straightforward case, just integrating h of x over that interval. Now that we've covered the basics of region integrals for two-dimensional areas, let's step it up to the third dimension. Imagine we have a three-dimensional region which we'll call D, as shown in the image. In this case, we're no longer looking at just an area, but the entire volume of this region. To calculate this volume, we use a triple integral over D. Volume equals the triple integral over D of dV, where dV represents a tiny volume element which is broken down into dx dy dz. This setup lets us find the total volume by adding up all these tiny volume elements within the three-dimensional region D. Just like before, we need to define the limits of our region, but this time in 3 dimensions. Let's start with z. The upper limit for z is given by a function h of x and y, which depends on both x and y. The lower limit, however, is simpler. It's just the xy plane, so z equals 0. This gives us the bounds for z as 0 is less than or equal to z, which is less than or equal to h of x and y. Now, let's take a closer look at the xy plane to better understand the limits for y and x. For y, we have two functions setting the bounds, g of x as the lower limit and f of x as the upper limit. So we get g of x is less than or equal to y, which is less than or equal to f of x. And finally, for x, our limits are from a to b, giving us a is less than or equal to x, which is less than or equal to b. With these limits in place, we're ready to set up our triple integral to find the volume over the three-dimensional region D. Now that we've defined our region D, we can set up our integral to find the volume. So our volume integral looks like this. Volume equals the integral from a to b of the integral from g of x to f of x of the integral from 0 to h of x and y of dz, dy dx. Again, I am using parentheses here to emphasize that we need to handle each variable's integral separately. We start with the innermost integral over z, since its limits depend on both x and y. Once we've completed the integration over z, we move to the next level and integrate with respect to y. We're not touching x yet because the y limits are still dependent on x. Finally, after handling y, we integrate with respect to x, which has the constant bounds a and b. By working our way outward like this, we calculate the total volume within our three-dimensional region D. All right, let's bring everything we've covered into practice with an example. Here, we're tasked with finding the volume under a hyperbolic paraboloid over a square region. The paraboloid itself is described by the function h of x and y equals x squared minus y squared plus 4. And the square region we're working over is defined by the bounds. -2 is less than or equal to y, which is less than or equal to 2, and -2 is less than or equal to x, which is less than or equal to 2. Our goal is to set up and evaluate the triple integral that will give us the volume under this surface across the area of this square in the xy plane. Perfect. Now, as we learned before, we can express the volume as a triple integral over the region D. Volume equals the triple integral over d of dv, where dv equals dx dy dz. For z, the upper limit is given by our function h of x and y, which equals x squared minus y squared plus 4, and the lower limit is just the xy plane, so z equals 0. This gives us 0 is less than or equal to z, which is less than or equal to h of x and y. For the square region in the xy plane, the bounds for y are -2 is less than or equal to y, which is less than or equal to 2. And for x, it's also -2 is less than or equal to x, which is less than or equal to 2. Now we can formally write out our volume integral. The volume is given by volume equals the integral from -2 to 2 of the integral from -2 to 2 of the integral from 0 to h of x and y of dz, dy, dx. We start with the innermost integral over z because its limits depend on both x and y. Once we've completed the integration over z, we move on to y and finally to x to complete the volume calculation. Now for the solution, here's our integration process. Step 1, first integrate with respect to z from 0 to h of x and y. The result is z evaluated from 0 to h of x and y, which equals x squared minus y squared plus 4. Step 2, next, integrate with respect to y from -2 to 2. The result of this integral is 8x squared plus 64 thirds. Step 3, finally, integrate with respect to x from -2 to 2. The result of this final integral is 64.